Welcome to your video on section 3.6, which is derivatives of logarithmic functions. In this section, we're going to imply implicit differentiation to find the derivatives of the natural logarithmic function, f of u equals e to the u, and the general logarithmic function, f of u equals a to the u. And then we will discuss another important method of differentiation called logarithmic differentiation. And we use that for the form of y equals algebra to some other chunk of algebra. But that's coming up in a second. Let's take a look at the derivative of the natural logarithmic function. Let's let y equal the natural log of x. This means, if we write it in exponential form, that e to the y equals x. Now let's take the derivative of both sides with respect to x. On this left side, I've got e to the y times y prime. On my right side, I've got 1. If I solve this for y prime, I end up with y prime equals 1 divided by e to the y. If I substitute my y value back in, and remember that y is equal to the natural log of x, then I get 1 over e to the natural log of x. Well, we know that those guys cancel each other, the e to the power of natural log of x, and the x just drops down. So y prime is going to be 1 over x. So if you're taking the derivative of the natural log of x, the derivative is going to be 1 over x. If you're taking the natural log of u, where remember, u is some chunk of algebra, not just a plain Jane x, then this is going to be u prime over u. In other words, you stick the argument in the denominator, and then you put the derivative of the argument in the numerator. Let's do a couple examples. So I'm going to take the derivative of both sides. Let's remind ourselves of the rule. The derivative of the natural log of u is u prime over u. So the u is the argument of the natural log, and that's x squared plus 5. U prime is where we just take the derivative of x squared plus 5, and we bring the power of 2 down, reduce the power of x by 1, and then we have both of our pieces. So y prime, in this case, is going to be my u prime over u, which means that y prime is equal to 2x all over x squared plus 5. Let's take a look at this next example. This one's a little bit more interesting. The argument of the logarithm is another function. So let's go ahead and look at, all right, I've got u is equal to the sine of x. So u prime is going to equal the cosine of x. So then the derivative with respect to x of this function is going to be, remember I put the argument in the denominator, and then I put the derivative of the argument in the top. But I'm not done with that because it simplifies into the cotangent function, because cosine over sine is cotangent. This problem is interesting. There's two ways you can do it. First way is quick, and that's to use logarithmic properties. Specifically, the logarithmic property that we're going to use involves the quotient. If I have a quotient inside the argument, that means I can split that up and subtract the logarithms. Then I can take the derivative. The second method is kind of long. And this one, you would leave it as is, and then you would just use the quotient rule for finding u prime. I'm going to tell you right now, that second method is just unnecessary. Use your logarithmic properties. It makes your life a lot easier. All right, let's show that. So I'm going to first rewrite the regular function. So it becomes the natural log of x plus 1 minus the natural log of the square root of x minus 2. I'm actually going to use one more property because of that square root. Also, it saves me a little bit of time, saves me from having to use the chain rule. Keep in mind that the square root is the 1/2 power. And keep in mind that for logarithms, if you have a power, that comes down as a constant. Let me just write that rule right here. If I have log base b with my argument of a to the power of p, that p just comes down in the front. These logarithmic properties are your friends, folks. Make sure you know them. Okay, now that I have it written in this form, now it's set up for me to take the derivative. So that's what I'm going to do. For this first one here, the argument is x plus 1. And I take the derivative of that, I'm just going to get 1. For this one, the argument is x minus 2. And the derivative of that is 1. And just don't forget that you've got this 1/2 that's in the front. So when I take this derivative, I'm really going to follow those rules. So g prime of x is going to be u prime over u prime over u. That's going to be 1 over x plus 1. And then I'm subtracting w prime over w. And then that 1/2 is in the front, which is really just the 2 in the denominator. And I'm going to have 2 times x minus 2 and 1 in my numerator. Now, unless I have to do some work with it, I really can leave my answer like this. But if I need to find horizontal tangents or anything, or do any other algebraic work with it, I should turn it into a simple fraction. So the way I'm going to do that is with LCDs. So my LCD here is going to be the product of both of those denominators, because both of those denominators are totally different. So the first one, this first one here, only has the x plus 1. So I'm going to multiply the numerator and the denominator by 2 and x minus 2. The second one here has the 2 and the x minus 2, but doesn't have the x plus 1. So I'm going to multiply the top and the bottom by the x plus 1. Now I need to distribute this out and distribute out the negative sign and combine like terms. So I'm going to have 2x minus x, which is going to give me x, and negative 4 minus 1, which is going to give me 5. And then the denominator is that 2x minus 2 times x plus 1. And that's my derivative in a simplified fraction. Well, all those problems that we just did were of the natural log. Well, what about logs of different bases? Well, let's recall the change of base formula. If I have log base a of x, I can turn that into the natural log of x divided by the natural log of a. And a is a number, so that's just like dividing by a constant. So if I want to find the derivative of log base a of x, it would just be 1 over that natural log of a times 1 over x, or 1 over x times natural log of a. In general, for u, where remember u is some chunk of algebra, then I can say it's like 1 over the natural log of a times u prime over u, or u prime over u times the natural log of a. So let's keep that derivative in mind. And look at this next example. So here, my base is 10. My argument is 2 plus the sine of x. So u prime is going to be the derivative of u. So the derivative of 2 is 0. The derivative of sine is cosine. So let's put that together. So u prime goes on the top. Then my u, and this u is a binomial, so it needs to be in parentheses. And then my natural log of a. And I can't simplify that anymore. So for logarithmic differentiation, it really is good for you to remember your log properties, okay? especially those ones that I mentioned on the previous parts of this lecture. I'm going to write them down really quickly. So once you have those logarithmic properties in mind, let's look at the steps of logarithmic differentiation. First of all, what you're going to do is you're going to take the ln of both sides. We call that the natural log. We're going to then simplify using the properties. So this is where these properties come in handy. We are then going to differentiate both sides with respect to x. We're then going to solve the resulting equation for y. Don't forget to substitute back in your original y equals whatever you started off with. Get that substitute. This logarithmic differentiation thing, you always use it for equations of this form. Specifically, if I have some algebra in the base and algebra in the exponent. So make sure that you know when to use logarithmic differentiation. All right, this one right here is a prime example. Got y equals x to the power of x. So the first thing I need to do is I need to take the natural log of both sides. Next, there isn't much simplifying to happen. The only rule I'm going to use is the power rule. So this power is going to come down in front. And again, that's this rule right here. If I have a p as a power in a logarithm, I write it down in front. That's what I'm going to do. Don't forget, on the left side and on the right side, the only thing that's changing is this x is coming down. Everybody still has a natural log. All right, my next step is I need to take the derivative with respect to x of both sides. All right, so I need to take the derivative of the natural log of y, and I need to take the derivative of x times the natural log of x. Notice on the right side, this thing is a product rule. This x right here is not inside a logarithm. So I can't use the product rule for logarithms. I have to use the derivative product rule. This other side right here, piece of cake. Okay, I just need to take the derivative of the logarithm. Okay, so on the left, I'm going to end up with y prime over y. The derivative on the right, I'm actually going to do it up here and then bring it down so I can simplify it easier. So this is going to be the first times the derivative of the second plus the derivative of first times the second. So and then when I multiply that together, x times 1 over x, that's just going to give me 1. And then plus 1 times natural log of x is going to give me natural log of x. But now I need to solve that for y prime. So I'm going to multiply both sides by y. I'm going to end up with y prime equals y times 1 plus the natural log of x. But remember, y is equal to x to the x. So I need to substitute that back in for this y here. So y prime equals x to the x times 1 plus the natural log of x. And that's my final answer. I don't want to. There we go. I was covering it up. All right, take a moment to use logarithmic differentiation to find the derivative of this function. Pause the video and see if you match my answer. Welcome back. Let's see if you have the correct answer. Okay, first thing we're going to do is we're going to take the natural log of both sides of this equation. When I take the natural log, the thing that I need to remember, and the whole reason why I do logarithmic differentiation, is that this power can now come down in the front. So that gets that pesky little thing outside of the exponent. All right, next, I need to take the derivative with respect to x of both sides. And let's not forget that we've got the product rule over here on the right side. So on the left side, the derivative of a logarithm is the derivative of the argument on top of the argument. Over here with the product rule, I'm going to do it up here on the second row for a second. It's the first times the derivative of the second, which the second is a logarithm, so it's sine in the denominator, and then the derivative of sine in the top, which gives me cosine of x, plus the derivative of my first times my second. If I simplify that, I've got x times the cotangent of x, because cosine over sine is cotangent, plus the natural log of the sine of x, because 1 times anything is just itself. And then I want to multiply both sides by y, so I can solve this for y prime. So on my left side, I've got y prime equals y times this x, cotangent of x plus the natural log of the sine of x. And then I need to remember y is equal to the sine of x. So this y right here, I'm going to replace that with my original function. And this ends up being y prime equals the sine of x to the x power times x cotangent of x plus the natural log of the sine of x. Got an extra example here because it's always good to see a few of these logarithmic differentiations. Again, this falls into the form. It's a ripe candidate for logarithmic differentiation because the form is where I've got algebra in the base in algebra in the exponent. So let's do it. I'm going to take the natural log of both sides. Next, I'm going to bring that cosine of x down in the front. And now I'm going to take the derivative of both sides. So I'm going to take the derivative of the left side, and I'm going to take the derivative of the right side. The derivative of a natural log is the argument underneath the derivative of the argument. Over here, remember, I have to use the product rule. So I'm going to do the first function times the derivative of the second function. The second function is the natural log, so I put the argument down here, and I put the derivative of the argument up here. And I'm going to add to this because product is plus for the product rule. And then I take the derivative of the first, and the derivative of cosine is the negative sine of x, times the second. It's not really much simplifying I can do from this point, so I'm just going to multiply both sides by y. And then kind of clean house as I go. So the y's cancel each other, and on the left side I just have the y prime. I'm going to write the y in the front, but I'm going to give myself some room. So this little y piece I'm going to put in the front, and that's my original function right here. Y is equal to 5x squared plus 3x to the power of cosine of x. And then I'm going to rewrite the stuff in the parentheses here, but I'm going to simplify this. If not simplify, I guess I'm at least going to write it as simply as I can, which, well, I guess isn't much. And that's what goes inside there. All right. And that tall drink of water, that's my answer. The basic differentiation rules. If you printed out the notes associated with this lecture, what I really would recommend doing is take this page, and use it as a quiz. See how many times you can print this out. Now this spans a couple of slides here, as you see. But in the notes, it's one page. See if you can fill it all out and get the correct answer. I'll put the correct answers in a moment. Okay, see if you can do this. Pause it, fill them out, see if we match. On your mark, get set, go. You back? Okay, good. Remember, the derivative of a constant is 0. Next, if you've got a constant times a function, constant just multiplies by the derivative of that function. Next, if you have the power rule, the power of n comes down in the front, and then you have x to the power of n minus 1. Remember, these are just plain Jane x's. These aren't chain rules right here. Next one, you've got e to the x. E to the plain Jane x, the derivative of that is just e to the plain Jane x. Natural log of x, the derivative of that is 1 over x. And the derivative of a to the power of x is 1 over the natural log of a times x. Next page. Again, go ahead and fill this out and see if we match. Hit pause and go. All right, welcome back. Let's see if we get the same answers. If I take the derivative of functions being added or subtracted to each other, I can add or subtract their derivatives. Number 8 is called the product rule. And if I have two functions or two chunks of algebra times each other, then I have to follow the product rule in order to find their derivative. The product rule is always the first times the derivative of the second, plus, because product is plus, the derivative of the first times the second. For number 9, this is the quotient rule. So for this one, I'm going to take my bottom, g, times the derivative of the top, minus my top times the derivative of the bottom. This is that low d high minus high d low. So low d high minus high d low. And then this is all over the bottom squared. Number 10 is where we start to see chain rule being used. Remember that U always stands for some chunk of algebra. Okay. This chunk of algebra could be like a trig function, or it could be a polynomial. It could be whatever. It's basically standing for something other than a plain Jane x. So, like the power rule that we had for number 3, this n comes down in the front, and then u stays the same. We reduce the power by 1, and then I multiply this whole thing by u prime. All right, the rest of the rules, they involve the chain rule. Well, I've already started to write them down, but go ahead, pause, see if you can fill this all out, unpause, see if you have the right answer. Best way to get good at these is just to write them down over and over and over again. Or I don't know, what do you use? What's your methodology for memorizing things? And you do have to memorize them. I know that sounds silly, but a lot of you are going to go into Calc 2. And when you go into Calc 2, you have to have your Calc 1 stuff memorized. Because in Calc 2, we do a lot of the opposite of the things that we're doing. I shouldn't say the opposite. We're undoing things. We're doing what's called the antiderivative in Calc 2. You get to see a little bit of that at the end of Calc 1. But the antiderivative means you have to know your derivatives, right? You can't undo something unless you know how to do it the first time, right? Okay. Same thing, pause, fill it out, see if we match. All right. Again, if it doesn't make sense, you can always go ahead and rewatch it. Show up to my Zoom meetings and ask me questions. It's a pleasure doing math with you. See you in the next video. Bye-bye.